because I'm seeing the number of students is very low. So when they do any seismic interpretation in oil companies, especially the geologists, for example, PDU, assign the work of seismic interpretation not to geophysicists, but rather to geologists. They believe geologists can do better when they do seismic interpretation, because they can correlate the seismic signature to the geology, to fractures, to faults, to structures, to stratigraphic features. They are more familiar with this rather than geophysicists. Geophysicists, they think of seismic section in different way. They think of seismic section. What is a seismic section, by the way? What is a seismic section? So these are seismic section. This is a seismic section. What you see here is a seismic section. So the first interesting thing is the faults. So this is a fault. This is another fault. Here is another fault. That's a couple of faults. This is one of the faults making graben structure, and so on. We consider this seismic section something which is resembling the real geology. And your task as a geologist or a petroleum engineer, rarely petroleum engineers do seismic interpretation. Your task usually is to follow these horizons. This is a horizon, or probably that's the one, the first one. Where does this horizon goes? There is a discontinuity, it falls down. That's the one. Let me choose another color, probably black or blue, maybe. This is my horizon. It stops here because there is a fault. It continues in here, down here. It stops here and continues down here. So your task usually as a geologist doing seismic interpretation or a geophysicist in an oil company to pick these horizons. This is a horizon. Horizons refers to the top of a structure, a rock, which was deposited in certain time, millions of years ago. So for the lab, for the first project, you will be asked to do these things. Nowadays, there are softwares, commercial softwares available, which can do these things automatically. Yani there is not much effort involved from your side. Those software is going to help you a lot doing seismic interpretation, picking the horizons. This is a horizon. So you should have a good eye to detect which horizon is which. So I started picking this one. Okay, I think this one goes down here. Why? Because there is a fault. There is another fault. So this goes again down here and it continues. It goes a little bit down and go again up. So then you try to guess where oil can be accumulated. Here probably, or here. That's usually is your task as a seismic interpreter. For the first lab, you will be doing seismic interpretation. So petroleum engineers might ask how I can benefit from these things. You will benefit, first of all, understanding what is seismic data. The data you will be given is a 3D seismic data. It's not 2D. That's state-of-art data. Nowadays, all the data, or majority of the data, are 3D data. I'm seeing a lot of students leaving, so let me check some names. Al-Fadl, Al-Maskari, Fadl, are you there?
Yes, doctor. Yes.
Good. Hamid, are you there?
Yes,
Hamid
doctor.
Al-Amri. Good.
Yes, doctor.
Doctor,
Yeah,
I'm present.
I'm presenting.
No, no, I am here. You're just
Okay. Oh, while let me see your name. Okay. Sorry, I got your name. No, so geologists, how they can benefit from these things? There are two stages to the project I will give you. The first stage is seismic interpretation, the thing I just explained, but I will explain it again later on in more details. You create maps, surfaces. This is a surface. It's in time because usually in seismic, everything in this domain is time domain. We learn what is time. And actually in oil industry, the only people who deals with time related to data are the geophysicists in oil industry. So this is the time. This is the time I send the energy and I wait for the energy to be reflecting back to the surface and being recorded by some instrument. That's the time. So usually they consider it two-way time because the energy goes down, hit the reflector, hit some interface between two rocks or a boundary between two rocks and get reflected back, going down, returning back, two-way time. Whereas this is just the surface or the distance from one point. We consider this thing as a real geology. We resemble this section as a geologic section. You remember, not sure when you have taken geology one, but if you have taken it in the last two semester, probably you've missed the chance of doing any field work. And during the field work, they take the students to some out group and they analyze the out group. They try to find where faults exist within the out group and how the layers are related to each other. So this is similar to what I think as an out group. Later, what you're gonna do, or for the project I give you at least, you get a map, and that's what you get usually in your final project. I'm considering, or this point is related to the petroleum engineering students. They do a final project in their 5th year, and usually consists of having surfaces, geologic surfaces, geologic maps or geologic surface, and they try to get how much oil is there. But we'll come back to this sometime later, maybe week 7, week 8. For the time being, I will distribute you into groups and start giving you the tasks and uploading in sometimes some videos showing you how you proceed with the project. For today, let's go back to our topic, which is seismic refraction, and try to complete seismic refraction. I do something, I stop the recording because I want to share this window. I have two windows. I want to share screen two. And I think we stopped last time somewhere here. I showed you all of these videos. I explained this thing. So whenever there is a shot point, a disturbance on the surface of the earth, we say the waves can travel in different directions. The simplest directions or ways they can travel are listed in here. There are 3 different paths they can travel. The first one is direct. The second one is reflected, and the last one is refracted. So what is the direct? Direct is the direct path from the source, which is a hammer or a vibroseis or whatever, to the geophone, to the receiver, or to the hydrophone. In case of water, if you're doing your survey in the water, the sensor is called hydrophone, whereas the sensor is called geophone in land surveys. It's the direct ray. And it travels with the velocity of second layer. It it travels in the first layer with the velocity of the second layer. Am I right? Am I right?
Again,
Guys.
please.
Uh, so don't get asleep. I think you have just eaten a lot of rice. So my question, the direct ray, it travels straight in a straight line between the source and receiver and travels with a speed. The speed is of which layer? Is it layer 1 or layer 2? In this case, in two-layer case, layer 1, layer 2.
One.
Layer 1.
Layer 1, yeah, that's true. It travels with the speed of layer 1. Let me just see what you are seeing exactly in the screen. Yeah, that's good. There is also reflections. Reflection is the ray which goes hit the boundary, that's the boundary, and get reflected back or received or recorded by the instrument. We call this thing a reflection. And this is the interest usually in oil industry. The energy we are actually interested on in oil industry is the reflection energy. Reflections is almost used 99% for oil exploration. Reflection energy. And we know the maximum reflections happens after the critical angle. This is the critical angle. And what's the critical angle? The critical angle is the angle when the ray hits the interface, it travels parallel to the interface. So the ray is traveling in the second layer. That's what we already talked about the last lecture. It travels in the second layer parallel to the interface and get exciting in its passage. It will excite some types of waves. We call them wavelets. And those excitations happens because of some principle which is called Huygens principle. The ray is traveling in the second layer. In its passage, it excites each particle. So the particle will generate energy in each direction. And some of those energy will travel back to the surface as head waves. As head waves. And get recorded by instruments. So there are three different waves. One of them is part of it is traveling in the second layer, which is the one among all of these three. One of them, part of its passage is in the second layer. Refracted. Yeah, that's true. Refracted. So refracted has some part of it in the second layer. So my question, if I'm standing here, what is the first energy I gonna receive? The
Direct.
direct? Yeah, the direct. That's true. Direct. You will receive the direct because coming to you straight. Let's assume at very, very long distance. Very long distance. Yani, let's say that this layer is very wide. What happens between direct and refracted? Which comes first?
Refracted.
Not
Direct.
I'm talking about direct or reflected. Which comes first? If this slab, if this direct, direct always comes first. But they will become very close to each other. Why is that? Let me make a drawing in here. So let's assume this is my layer. It's so large. So this is the direct, and this is the reflected. Reflected. So after long distance, this becomes almost a straight line. The reflected gonna be almost like a straight line. Reflected is not the first to arrive. Reflected energy will not arrive to any geophone as the first. Whatever the distance, this is the distance. This is the distance from source to receiver. That's we call it offset or distance. That's the X. This is the Z, thickness. This is always this vertical thickness or this thickness. So this is the thickness of layer 1. It's not depth. In this case, it's depth to second layer. But in some other cases, whenever I have more than one layer, that's not the depth to a layer. That's the thickness of each respective layer. We'll come back to this point. So this is the direct energy. It's usually the first to arrive, except at some distance. The refracted will overcome the direct in some point. We'll come to this point later on. So the only energy which is traveling, some part of it traveling in the second layer is the refracted energy.
Doctor,
Yes,
why is there here in this figure, I mean, why refracted doesn't penetrate layer 2?
there is. So if I draw it, there is some goes like that. But at this specific angle, we call it a critical refraction. There are other refractions, normal refractions. If they does not go to the layer, second layers, we can always just see the first layer. And thus seismic is useless. Seismic method is useless because I can only image the first layer. There is this, the energy is traveling in every direction. So it's traveling in all directions. But I'm taking only one part. After this critical distance, this is the critical distance. After this distance from here to here, most of the energy is reflected. There is nothing transmitted. Whereas before this distance from source to this point, most of the energy is transmitted. We already talked about this total internal reflection or subcritical reflection. So how I can draw them? Yani I'm counting the time. I'm sending the energy, I'm counting the time. I don't know where it goes. When I send something, I don't go where exactly in the earth it goes. I only can do one thing. Detect the time I receive it back. I send the energy, just wait, get the time. How long it takes for the energy to travel in the subsurface and get reflected or received by the instrument. That's what usually you just record. With amplitude, amplitude data will not consider amplitude data for the time being. So you generate something what we call TX diagram. That's what we see. The X is the distance from source to geophone. So in this case, I'm having one geophone, but in reality, you will have more than one geophone. There is one geophone here, one geophone here, one geophone here, and so on. For example, the instrument we have, it has in our department, it has 24 geophones. In real seismic exploration for oil industry, usually they have hundreds or tens of thousands, 20,000, 50,000 geophones. So the number is large. in real oil field exploration, whereas the one we have is just for study. We will not do oil exploration. We cannot do oil exploration with the equipment we have. The idea is just to get the students to know how to operate these things and correlate them or to their studies, to the theory they study with some applications. So you have usually many geophones.
Doctor,
Yeah.
what is the answer of this question?
Which question?
This one.
Why are there raised straight lines? Why are there straight lines? You can tell.
Maybe because it's a light and the photons travel along a line.
Because the velocity in each layer is a homogeneous layer. It's one layer. It's one velocity. So the wavefront is traveling in each direction homogeneously, uniformly. And we know the ray front or the ray is perpendicular to what? Wavefront. This is a ray, whereas this is the wavefront. So they travel straight lines in homogeneous layer. If this layer is not single velocity, it's very complex velocity, the ray will not travel straight line. Is that clear? That's what will take us to the seismology course. We said why in reality we have arrival times like this instead of being straight. Because the earth is not homogeneous, it's made up of different layers, or each layer having its own velocity. You remember this? There was a slide in, let me show it to you. I think it's in seismology. Yeah, this is the observed, they are curved. Whereas this is the, if the earth is homogeneous. But the earth is not homogeneous. The earth is made up of different layers, and the layer of each, or the velocity of each layer, is different. And that's the answer, because each layer in this simple case is homogeneous. So the ray travels in there as a straight line, and travels in the second layer as also as a straight line. So when I record many geophones with many geophones, I get only the first, yani, let's assume that there was a geophone here. The first energy it receives is this direct. So how it looks like, it's a trace usually, it's a wavelet. So what you get, this is the distance, that's its location in this distance from zero, source is at zero, and the geophone at some distance. And what I'm recording the time. So what I get, there is no energy arrived. It took some time. It took from here to here some time. That's the time. And start when the energy arrives, it starts shaking. This is the first onset of shaking. The first energy arrived here is direct. Whatever arrives later on, I usually care about it. But for this refraction case, we don't care about it. Because there is also some other energies which goes right away are reflected back, which is this refraction. This was for the first geophone here. Let's assume there is another geophone here. Since this is farther away from the source, the energy haven't arrived. My trace is straight line, straight line, straight line. After some time, the energy arrived. There was started some shaking with the ground. So it recorded. This is the spacing, real spacing between this geophone and this geophone. This is the real earth. So it arrived first here, then arrived here. Why you say the shaking haven't stopped? Why there is still some shaking? Because the energy is coming also as reflected energy. Not from just this layer. There are other layers as well. Go deeper, go deeper. They are all coming, but coming later. Maybe there is another deep, strong reflection. It generated this strong amplitude for me. But what we care right now for refraction, we care about first arrivals. First, this is the first. There was nothing. Which arrived first? What energy is arriving first at this geophone? Who can tell me? What energy is arriving first?
Direct.
Direct. True. So direct is arriving first. So this is direct. Let's say this is the slope of direct. The direct is arriving first. So this is the critical distance. This distance, we call it critical distance. At this distance exactly, here, I start receiving critical or critically refracted energy. What is this distance? This is this energy. So this distance from here to here, I call it, this distance is go reflected back. There is the first critical angle is what we call critical distance. As critical distance. The critical distance is the distance a refracted energy starts appearing. You see, if I draw this line, it's dashed. It means it's just an interpolation. It's not a real energy. It becomes continuous line after the critical. So this is the critical angle. And from here onward, the energy, refracted energy, will start going parallel to the interface. And head waves start appearing. So those are head waves. So it's not one geophone. There is also one geophone, so on. And there is also one here. So the question here, the question it asks, in this graph, let me continue, Yani, before we go to the questions. Let me give you some insights. I, as a geophysicist or geologist, what do I usually do with these graphs? I start pick. I start draw a point here. First breaks. Let's assume there is another one. There is another one here. There are many geophones. I always go pick. Then I draw continuous line along these first breaks. First, why they call them first breaks? Because they are the first to arrive. What is the first to arrive at this line is the direct. The direct energy is the first to arrive to the geophones. All these geophones, still the direct is the first. Up to a point. Up to point, what we call that point? What we call that point?
Critical.
I'm pointing to it.
Crossover distance.
Crossover distance. So after crossover, what happens? If I go back to the previous slide, after some distance, because second layer is faster, is way faster than the first layer, the energy traveled, the refracted traveled faster in the second layer, so it overcome, it will arrive earlier than the direct to the geophone after some distance. And that distance is called what? What's called? You just said it.
Crossover.
crossover.
Yes.
Yeah, and after some distance, because the refracted energy is traveling in the second layer with a higher speed than the first layer. So at some point, it will arrive earlier. So I'm in the queue, I'm trying to go to, for example, to Mabela, but I'm taking some part of my movement, I'm moving slowly. But later on, I take, for example, high road. I go to the high road or Muscat Express, what they call it exactly, I'm not sure. High Expressway or Shara Sari. So I go to Mabela with someone else is moving slowly but straight line. In few meters, in few up to Khod or in these regions, he will arrive. He's always earlier than me. But at Mabela, I go take the high speed road. I might overcome him. Even though I'm in short distance, I'm traveling slower than him. So that's the reason at some point, refracted energy will become the first to arrive. And that's what you see here. So the geophones here, they will detect nothing, no energy arrived. Up to this point, energy start arriving. And I as geophysicist pick the first arrival because it's easy to pick. It's calm area. It's a straight line before the first energy. So first energy is easy to pick. You as a geophysicist, in your next lab, you'll be doing some picking, real picking. So you pick this energy. There are many of them. Let's assume there are a lot of geophones, and you draw straight lines. You draw a line connecting these points. Those points are actually first arrival points. So let's go to these questions. I think by now you know how these lines are drawn, how I can correlate between the TX diagram and between a real cross section like this. This is what we call TX diagram. So if I erase everything, my first question, why they are asymptotic? Oh, first, before that, how I can get the velocity from these lines, especially the straight lines. So this is distance.
From the slope?
Yeah. This is distance. This is time. So slope is what? Slope is الفرق في الصادات over الفرق في السينات. So that's what you give you the slope. However, I need what? The velocity. Velocity is distance over time. So it's the reciprocal of slope. Or slope is the reciprocal of velocity. The opposite. يعني. So the direct, it gives you velocity of which layer? The direct is traveling in which layer?
First.
First. So its slope gives you the velocity of first layer. Yeah. The first refracted gives you the velocity of which layer?
Also the first.
Majority of it is traveling in second layer. So this line is slope of the refracted. This is the refracted energy. So it's arriving before the direct. The direct is later. So here is, if I draw a line, which is the first? The refracted. Which is the second? The direct. Then what comes? Reflected. At very far distance, far, they become asymptotic. They never touch each other, but they become very close. Reflected and direct. because simply because if this layer is so thin, it's so large, يعني, the direct and reflected, they almost become يعني, the same. Reflected is this one, because where a direct is the straight line. The difference is very small in time at very far distances, and that's the reason you'll find them becoming asymptotic. They will not touch each other, but they become very close to each other. The reflected will never start at zero. None of these start at zero. The only energy start or go through the zero in TX diagram is the direct. Because direct, if I put a geophone here, I can directly record it. But this geophone, it will never record a refraction. There is a refraction happens after the critical. So critical, this is the critical. Refraction only happens after this critical. The reflection, when it happens, the reflection is this way. It goes down, hit the interface and returns back. So this is the time, and this time is simply 2h over v1. Why 2h? Because it went down and returned back. It went down for the reflection. This is the reflection line. It's not a straight line. The reflection line is not a straight line. A refraction and direct, they are straight. Why it's not straight? We'll study that in a reflection technique next week. So the first question, the answer to the first question, how I get the velocity of respective layers, layer 1, layer 2, and layer 3, and so on, just simply by the slope of those lines in TX diagram. The direct gives you the velocity of the first. The refraction gives you the velocity of the second layer. You might ask, what if there are more than 2 layers? Yeah, we'll come back to this point later on. Why the direct is straight line? Because traveling in one layer as a straight line, directly from source to receiver in a straight line. So it's a straight line in TX diagram as well. And it should go through the origin. Why the origin? Because if the source and receiver, which is not possible, but if I source and receiver at exactly the same point, how much time it takes for the energy to receive this, to be received by this geophone? If they are on the same point, zero. Yeah, they are on the same point. So the direct ideally or theoretically can be zero. If those two are in the same point, because I'm drawing connecting the lines. Maybe there was no geophone in here, but there was a geophone here, and so on. When I connect them, I see it's going through the origin. Connect a line through them, those points, I'll find this is going through the origin. But reflection itself, it will not go through zero because it has to go hit the interface and returns back. And that's the time. Especially this time. It goes directly down and return back. Directly straight down and return back. That's the time in this case is 2h1 over the velocity of first layer. But it becomes much more complex for other reflection. For example, this reflection, the time is more complex. We'll not study the time for reflection for non-zero offset. What's zero offset? Zero offset, this is zero offset. And it's the source and receiver at the same location. We call offset is zero. And there is no offset between the source and receiver. They're happening at the same point. So we answered this question. Why is a refracted ray is a straight line? It's also straight because it's traveling in a straight path in the first layer, and it's following what it's moving also as a straight line in the second layer. And why the refracted does not start at origin? Because they have to be or start to be recorded after the critical refraction. After the critical refraction, you start getting, after the critical distance, you start getting refracted energy, but they are not the first. So if I draw a line, the geophone, probably if there is a geophone, this is the first energy received. The second is the refracted energy, but it's not the first. The first is still direct. Here, the first is the refracted. And what that distance is? Crossover distance. Crossover. From the name crossover, it means the direct moved in a second layer with high speed and start taking over the first layer of the direct ray, which was traveling only in the first layer with lower speed. It will start to become the first to be received by a geophone at far distance or at some distance. And that distance is supposed to be higher than the crossover distance. The crossover distance is the distance then between the source and receiver. And the last question says, why is the reflected array is asymptotic to direct ray? Because it will never be the first. It will never, the reflected will never be the first. But at far distances, it almost, the line almost look like a straight line, which is what the straight line is, the direct ray, actually. Is that clear? So the important things, the takeaways, how we get the velocity of respective layers. It can be obtained from the slope of each line. Those are the lines. You can get the velocity of each layer. So this is something really amazing because you are not digging anything into the ground, yet you are able to know how many layers are there. Quite interesting. Geophysics start becoming something very useful. Without digging, just doing simple studies like refraction study, and you can tell how many layers are there. So how we draw it, how they are drawn. So for the direct ray, which is this line, the red line, the equation or the governing equation is simply the distance over velocity of the first layer. So it's straight line. Reflected, it's quite different. Its equation is different. It becomes asymptotic. It becomes asymptotic to the direct ray. And the intercept here with the y-axis is simply this value. That's the time, because this y-axis is the time, and this is representing this line, this portion. Goes down and returns back, and this is h. The thickness is h. So that's the reason I have h1. y2 because it goes down and returns back. And with what speed it travels in this layer? With the speed of first layer. But exactly at normal incident, goes down and reflect back. Whereas in other distances, the formula is quite different. We'll come back to the formula of a reflection. The refracted energy happens after the critical angle. That's the critical or critical distance. This is the critical angle, whereas this distance is the critical distance. It's critical distance. And the governing equation is simply this one. Try to remember this one. The governing equation is this one. So this is the equation of refraction. In the lab, next lab, the first part will be what? I will ask you to derive this equation. I never asked students before driving this equation, but I'll give you some hint. If you can't do it, then it's fine. I might do it for you then. But this is the equation of the refracted energy. The refracted energy after the crossover distance is the first to arrive. That's the time, this is the distance. So it's the first to arrive after the crossover. It's always the first. The first energy is the refracted energy after crossover distance. Before crossover, the direct is the first energy to arrive. And the governing equation is simply this equation. It has two parts. The first part is x over 2v2, velocity of the second layer, whereas the first part is the intercept, is equal to intercept time. That's the intercept time. This is the time if I project this line along the y-axis, the intercept is equal, that time is equal to this value. So I have, this is what usually I get. Usually in my refraction survey, this is the thing I get. This is the map or thing. So the question, you have T intercept from the refraction equals what? Equals 2h1 over 1 over v1 squared minus 1 over v2 squared. What I need, what is my objective, what I'm interested in from this equation? This equation, T-intercept equals 2h1 square root of 1 over v1 squared minus 1 over v2 squared. What's my objective? What is the value I'm interested in? Who can tell? Time I record the time. V1 I recorded, although I can get it. It's simple thing, I can get it easily. I get the V1 and V2, Mariam is saying V1 or V2, I get them from the slopes. This slope gives me V1, this slope gives me H. Yes, the thickness of first layer. That's what you need. The intercept, you calculate it from here, from your graph. This is what you usually record. You will not see this thing. That's not something you'll be seeing. This is below your feet. You don't know where the rays are traveling. You will record this thing, the TX diagram. And what you are interested on? You are interested on the thickness of first layer. You get the velocity of first layer from the slope, the velocity of second layer from the refracted energy. Slope of direct gives you the velocity of first layer. Slope of refracted energy, first refraction, gives you the velocity of second layer. The intercept time, you just extrapolate this refraction line and make it pass through the y line. the y-axis. The intercept point is t, we call it tn. T-intercept or time intercept. This, all of it is equal to this value. And what we have, we already know what's V1. We already know what's V2. We calculated them from slope. We already know the T-intercept. That's the intercept time. We just found it. How much is it? Let's say it's 1 to 2.5, whatever, millisecond or microsecond or in time, in second probably, whatever. But you got these values. What's remaining is H. So you get the thickness of first layer by simply doing analysis of TX diagram. And usually how we create this TX diagram, how they look like in reality, and how you create them. That's how you create them. So this is a real seismic section. It's a seismic record. So you see here was a geophone. These are all geophones. 1, 2, 3, 4, and so on. Each line is a geophone. How is that? That's the one. So there was, this is a source. This is 1, 2, 3, 4, 5, and so on. So each one generate, it's recording a trace, a line, a trace. So each one is a geophone, representing a geophone. So this one, the direct goes straight line, start recorded here. So the first geophone is here. It was maybe close, so there is not much time. You see almost a zero start. So the direct goes and hit this geophone and I get a break. I get energy. The second one, it goes sometime, the ray goes sometime and start recorded. There are other energy, but they are arriving later. Maybe this energy reflected, which is arriving here or here. For the time being, I'm interested on the first arrivals, something arriving the first thing to my geophones. So all geophones, this is the third one. So this is the third one. Took some time. The energy, the first energy arrived is the direct. So this is the direct. It goes through the zero. And so on. If I ask you how many geophones are there, how many geophones was in this acquisition? Who can tell me? It's simply counting the number of these traces. These are traces. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So there were 17 geophones. You draw them, you pick first breaks. The lines are drawn actually. The lines are drawn by you. Those interpretations were made by you. This is the real, the black thing is the real thing. Is the thing which is recorded by the instruments, by the system, the black color. The other colors are your interpretation, your geophysics interpretation. You draw lines, you make first breaks and a draw line. You make another first break. Oh, you see, okay, this is a different slope than the first one. You think, okay, this is probably a refracted energy. So this is at some time, the refracted start happening or some longer distance. Those refractions start happening. So this distance here is crossover distance. Because why? The refracted is the first to arrive. The slope, then you calculate, you create this TX diagram. This is exactly this one without those traces. I remove those traces. So I kept only the points and the lines. So this is the intercept time. This time equated with this value to get the H. And how you get the velocities? Velocity is simply the slope of this one, the slope of this one. So this velocity is simply meter, how much meter from here to here, divided by time. How much time from here to here. And in this case, for the direct, the same way. How much distance from here to here to go 250 meters divided by 0.42 seconds. This gives you the velocity. Velocity is the x over y. This gives you velocity, but slope usually is y. Slope is usually y over x. Slope is y over x. So the slope is the reciprocal of velocity. What is time over distance usually? Reciprocal of velocity. What is reciprocal of velocity? Let me ask the petroleum engineers. What is this value, 1 over v?
Time over distance.
Yeah, but what they name it in petroleum engineers, in petroleum engineering? Who can tell? Have you heard of this term? Huh? Have you heard of this term? The thing I have written in the chat. Slowness. Really? What sonic log? What it does read? What sonic log gives? Have you finished formation evaluation course?
We are doing it this semester.
Okay, so my bad. So sonic logs gives you actually slowness, which is reciprocal of velocity. Sonic logs gives you slowness, which is reciprocal of velocity. So you get the velocities and you plug them here in this equation to get the thickness. And then you have a model. You have a model of Earth. You say the Earth is made up of 2 layers. The velocity of respective layers is blah blah, and the thickness of first layer is that much. That's what we call a model, a geophysical model of the Earth, based on your geophysical analysis. Why you care about these things? Why I care? Because when people try to build a tall building, a long story building, what they do, the first layer is very unconsolidated layer. The first topmost layer is gravel, is mud. The deeper layers, once you go deep, you will find hard rock, a bedrock. In Al-Batna, that's what we see. In Muscat, no. We already start with the bedrock, because in Muscat, the sedimentary rock or the igneous rock or metamorphic rock, it changed from one place to another place, are on the surface. Whereas in Batna, we have sabkha. So sabkha is very thick layer. And how you get the thickness of that sabkha? You can do refraction methods. You can do refraction method to get the thickness of the sabkha. And why I'm interested in that? Have you heard of Blue City in Sawadi? Who have heard of Blue City and Sawadi? Anybody? المدينة الزرقاء.
المدينة اللي ما شافت النور.
Huh? They haven't made it. The project haven't finished. They stopped the project. And one of the main reasons the budget start increasing. Why the budget started increasing? Because whenever they try to build, they find the foundation is not stable. The ground is sinking down. They could have avoided that if they have done seismic methods or geophysical methods to understand how thick is the sabkha. The area there in where they're trying to build, where they tried actually, they stopped the project, Medina Zarqa. It's supposed to be built in the Sawadi region. They stopped it because the foundation are sinking down. How to make the foundation stable? They have to make deep excavation and put their foundation very deep. Why they put them very deep? Because the bedrock is quite deep. You need to dig into the bedrock and put your foundations, the cement and the steel there into the foundation to make your building stable. The area there is a khor. يعني ما يدخل ويطلع. So they have to remove all this sand to get to the bedrock. And it's quite deep. They needed more money. And the government thought later on, oh, we are wasting our money in something which is later on becoming not economic for us. They stopped the project. They never did any seismic or geophysical methods. They could have spent some money and contracted some people who can do seismic surveys and later on tell you how deep is your bedrock. What is the value of this H, which is the bedrock, thickness to the bedrock. That's what I'm interested on. The whole project failed because they haven't made geophysical surveys. If you're building a home, a simple home, you are not wasting, for personal, for myself or you, we are wasting big money, big chunk of money. But for government, no. The government, they have the budget to make seismic surveys instead of making their projects disasters later on. So how it usually done? What is it that simple? No. Usually what you get is such a thing. So you see these lines, they're all geophones. The energy first arrive. This is the first arrive. And this is the location of the source. It's exactly what you see here. But that's the one in real thing. You draw lines. You pick the first break and draw line. This is the direct. This is the refracted, first refracted. There are two ways to get, there are two equations. For your case, just let me remove this equation. You use the first equation always. Just use this equation. That's the equation of refracted energy. The refracted energy, time of refracted energy is following or governed by this equation. And in reality, that's what you do. And in your next lab, I will be giving you a profile, a shot together, similar to what you see here. And you need to pick first breaks. Get their velocities, get the velocity, and enter or extrapolate this line here. So this is the intercept for the refraction. This is the refraction. This is the direct. Extrapolate it, get the value, equate it with what? Equate it with this value, with only this part. So you already have right now V1, V2. P-intercept is recorded as well from here. What's missing? The H. If I ask you, can you get the critical angle? Can you get the critical angle? Yeah, sine of critical angle is equal V1 over V2. So this is V1. You already got them or found them from the slopes. The critical angle can be found easily. This distance here, you see the refraction is the first to arrive Who can tell me what this distance is? The refraction is the first to arrive. Crossover distance. This is crossover distance. Somewhere here, because not first, somewhere here we'll find some other distance. We call it what? We call it critical distance. Here somewhere, I'm not sure where exactly it is, but they name it critical distance. It's not the first to arrive. Yes, critical distance. That's really good. You are doing better than the previous semester, I believe, at least. According to my observations, you are familiar with what I'm talking to, or talking about what exactly, because the last semester when I asked them simple questions after explanation, they couldn't understand exactly what I was saying. So this is very important thing for geophysical studies, and this is what usually the type of data you receive. That's the type of data you receive. Sometimes I get this one here, airwave. So sometimes if you just need to get this one upside down. Sometimes you find them like that. And this is direct, this is refracted. There is a wave called air wave. What is air wave? I go back to my seismic section. So air wave is actually the wave traveling in the air, not in the first layer. It's traveling in the air and getting received or recorded by geophones. That's what we call air wave, and that's what you see actually in this section. That's the air wave. What is the velocity of seismic waves, or velocity of waves, not seismic, waves in air? What's sound speed? Who can tell me? The speed of wave in air. Who can tell? It's about 300 meter per second. Yep. Yep. All those answers are right. 330, 360, 300. So this is the speed at which wave travels. Speed of wave in air. So if you go to this line, or not this one, and try to get what is the velocity from the slope, you'll find its velocity is almost like close to 330, 360, or 350. It depends on the moisture content in the air. How much moisture is there? If there is high moisture, the velocity will increase a bit. If the air is dry totally, the velocity get close to 300 meter per second. So the seismic can even tell you, you see seismic section, they can tell you even the velocity of air. And this is, if I ask you, what is this? What I regard it? Is it signal or noise? Sound, not light. Malik, that's sound wave, not light wave. Light wave is so faster. Noise, yeah. Air wave is noise. Air wave is right now noise. Ground rule, or what ground rule, usually they are surface wave. Rayleigh and love wave, they are ground rules. They name them ground rules. You remember when I said ground rules, they are low in velocity. Yeah, draw a line. You see slope is high slope, steep slope. Steep slope is high, so velocity is low because they are reciprocal of each other. Yeah, Osama Al-Maqbal asking, what's the difference between air wave and direct wave? Air wave travels in the air. So if I go back here, air wave travels in the air, whereas direct waves travels in the first layer. Which is faster, this one or this one? Air wave or velocity in the rock?
Airwave. Or direct.
Direct.
It will be the direct because
Yeah.
of the higher.
Higher velocity, yes. Anything harder becomes the velocity in it gonna be harder. The velocity in rocks is harder than the velocity or the speed of waves in rocks. Harder material is faster. And rock velocity of waves in water, P wave, is almost 1,500. But in sedimentary rocks, the velocity of P wave is 300 or 3,000 kilometers per meter per hour. 3,000 kilometer per hour in sedimentary rocks. In igneous rocks, it becomes way higher. So this is way slower than the velocity here. And that's what we have seen already. Here, yani, you see which one is gentler. Maybe they are, maybe they are in this case at least. No, should try to find another line. This is the air wave. These are direct refraction. There are many such sections you see. Why you see this section? Why you see it like that? Why you see it's going in the both direction? Why? Because in this case, in this simple case, in that case, what you see here, what happened? The acquisition made like that. So there were a lot of geophones. And shot was here in the middle. So it went all direction. And so on. So this is what you see. That's what you see.
Doctor,
Yeah.
go to the slide, please. The second law, T equal x over v2 plus 2h1.
Yes.
For what we use this law?
When to use this law? If I ask you a question, okay, you found the velocities from the slopes, am I right?
Yes.
Okay, you found the times from the velocities from the slope. You found the thickness of layer from the intercept, am I right? Using this
Yes.
equation. So my question, I might ask a question in the exam or in the quiz. What is the first arrival at some distance x? Let's say 200. What is the first arrival? By convention, you will know that it's not reflected energy, but it could be either two things, which are, what are these
Direct
two
or
things? Direct or refracted. So direct, the time of direct is what? Distance over
V1.
velocity. V1, yes. So you plug this one, you get the time. Whereas for this one, for refracted, you use this one. You already have H, you already have V1, V2. You plug this value, you get the time. See which one is the lowest.
But the time is the same for time direct way, direct ray.
No, the time is different. So you see here, which time? This is the time of refraction. This is the time of direct. So maybe this is 200, 200. The lowest one, the lower value is the first arrival. The lower time value of time is the first arrival. So I ask you this question, you did all the things, you got your values. I ask you, what is the first arrival? What is the energy which is the first arrival? At some distance, let's say that distance is 100 meters. You use these two equations. This is for direct. You know it's not refracted, reflected energy. You can say it's either, yeah, this is for only reflection, Mariam. Tells you the time of reflection at any distance. Quite useful.
Doctor, the red line for direct ray.
Yes. The green is for refracted. Direct always goes through the origin. We don't consider for the time, never ask questions about reflections because there is a dedicated lecture for reflection, which is the blue curve. So that's how it is useful. If you, what is the difference between direct and the equations only for, yeah. Mariam Ghafri is asking how we can use this equation. That's how you use it. And why I need it, why I care about it. Usually you do something we call simulation in geophysics, forward modeling. Forward modeling. What is forward modeling? I know the equations. I know how the wave travels. What equation it follows? It follows this equation. So you say, okay, I have two layers. The thickness of first layer is that much. The velocity of this first layer is that much. The velocity of second layer is that much. And you give these to some computer or Excel and ask Excel to calculate the times. What you are doing, you don't know the real Earth, you guess the Earth. No, I have an Earth which is made of two layers. The first layer has that much velocity. The second layer have a velocity of blah, and that's the thickness of first layer. Plug this number to this equation, you make forward modeling. With Excel, simple, yani. Keep one line, one X, and then the other one is velocity, V1, V2, they are, what is changing? X is changing. X is changing. X is different here, different here, different here. But V is one value, V1 is one value, V2 is one value, thickness is one value, and you get different times. Why you care about this equation? That's what we do in computer. Excel can do it for you. You don't need to create a sophisticated program. And that's how we usually do some advanced seismic analysis. Not just geophysical, all if you know the governing equation behind something, you can simulate it. You make a simulation. And that's actually, if you hear anything related to simulation, that's simulation. Earth simulation, that's how we do Earth simulation. We know the equation, we give a guess of something, a model, plug in these numbers, see what the results are. Is that clear? So let's move forward.
Yes.
What was the question? And let me tell you something, how is that important? Whenever we do these equations, this modeling or this simulation, we are trying actually to guess the real Earth. You usually you will do as a geophysicist? You go to the field, acquire data, acquire some real data. You are, as a geophysicist or a geologist, your task, or in petroleum, your task is to know the earth. So the data you observed or recorded, they are actually times. They are times. Everything is a time, in geophysics, especially in seismic, in time domain. You make a guess. You observe time. You make a guess and observe time. You have real times you acquired from the field. You compare them. If they are good, they are matching, it means the model you guessed is correct, is close to the geology, real geology, or cannot be exactly the same as the real geology. Impossible. But it's very close to the real geology.
Doctor, we get the velocity from the red line and the second velocity from the green line.
Green line. Yes. Velocity of second layer from the green line. The velocity of first line from the red line, which is direct ray.
Okay, thank you.
These lines are not red and green by default. You draw them. That's what you get. In reality, this is what you get. These traces. You draw these lines. This is, for example, that's the red line. The line you talked about. And this is the green line. Is that clear? That's what you get. These are the traces is actually what you get from your acquisition, field acquisition. Those lines are your interpretation. Maybe I give the same section, this shot gather, the name is shot gather. This is called shot gather. If I give it to two different persons, each one will come with slightly different velocity. That's fine. And that's the reason we said geophysics have some uncertainty. Maybe there was some noise, the picking wasn't easy thing, and you need to pick them. You need to go and pick the first time arrivals. So two people will come up with two slightly different models. So what about multiple layers? Earth is not one layer. It's made up of multiple layers. If the layers are horizontal, as is the case, and the velocity is increasing as we go deeper, so what you get many different straight line with what? With decreasing slope. High slope, lower slope, lower slope, lower slope. How many lines are there? There are 4 lines. This is the first line gives you the velocity of first layer. The second line will give you the velocity of second layer. This is the first refraction. First refraction. This is the second refraction, third refraction. Why third refraction? What is this one? What is this line? Who can tell me? Is this a refraction line? That's direct. Yes. This is direct. This is the direct ray. This is first refraction. Second refraction, third refraction. We said first refraction, as we have seen already, the first refraction, this is a two-layer case, one layer, two layer. The first refraction gives me the velocity of second layer. First refraction gives me the velocity of second layer. Second refraction gives me the velocity of third layer. Third refraction gives me the velocity of fourth layer. And how many thicknesses I get? These are the thicknesses. Now, this P-intercept here gives me the thickness of first layer. First layer. Thickness of this intercept from second refraction gives me the thickness of third layer. This layer. Sorry, second layer. This gives you the first layer, thickness of first layer. This gives you thickness of second layer, not depth, thickness. How to get the depth then? You add them together. Add this thickness from here to thickness from here. You get depth. So again, I might be confusing you. The first intercept gives you the thickness of first layer. Second intercept, second refraction, this is first refraction, second refraction, you just extrapolate straight line and let it intersect with the y-axis and get the thickness of the second layer. The third intercept gives you the thickness of third layer. Can I get the thickness of fourth layer? No. I need then another refraction. No. Yes. Because I need another refraction line. So this is how you can easily work out the velocity of many layers. But thickness is not that simple. And to get the thickness from second layer, you need actually the thickness of first layer. How is that? I tell you now. So this is a multiple layer. We don't consider this equation. I might do some editing because this equation is similar to this equation. This part especially, they can give you the same thing. Yeah, we'll come to this, Azan. What if the layers are tilted? We'll start with the easy things, we then move to difficult things. So what you do, you get this one from here. Intercept one, you get it from this time. You already have this TX diagram. You made it from your shot together. Velocity you obtained from direct and first refraction, you get the H. That's how you rewrite the equation. And you get the H, divide both sides by this. And that's how you get the equation, the thickness of first layer. You once obtain the thickness of first layer, you have the thickness of first layer, try to find the thickness of second layer. How is that? The thickness from this one, this intercept is not only this one, is combination of first one, which is this one, combination of first one plus a new term, plus 2H2, thickness 2, multiplied by square root of second layer minus 1 over V of third layer, and so on. So if I ask you a question, what is the intercept time for third layer? What is the thickness? How you get the thickness of third layer? What do you do?
Vector, why we do plus here or the H1 and the H2? You need only H2.
Yeah, but the equation actually for intercept 2 include H1. It includes, so intercept 3 equals intercept 1 plus intercept 2 plus 2H3 over 1 over V3 minus 1 over V4. You got that?
I mean, Doctor, we need the height of the layer, not all the height from layer 1 and 2, both together. So that so now we only measure all the height for 2 layers if we add them. I mean,
no, you bring this one, you bring this value to here. First, you bring this value to here. This is This intercept 3, it includes many intercept plus this value. So if I ignore these two, the equality is not true. Let me, maybe it's not clear to you. I'll explain it with different red color probably. So to get the thickness from first layer, for the first layer, I get calculate this intercept. The value of this intercept is simply is equal to H1 over 1 over V1 squared minus 1 over V2 squared. Is that clear? So this gives me what? I already have this, gives me the thickness of first layer. That's what I need. Let's assume I want the thickness of second layer from here. So this actually is what T intercept 2 is 2H1 over 1 over V1 squared minus 1 over V2 squared plus 2H2 1 over V2 squared minus 1 over V3 squared. So if I ask you to get this value H, you need first to get H1. If you want to get H2, you need first to get H1. You need to get V1, V2, and V3. V1, V2, which is here, and V3. So you calculate first this one, this intercept, and then calculate this intercept. Is that right? Is that right? Mariam is saying no. Then it's somehow right or somehow wrong. What's wrong? Wrong, you are complicating yourself, because if you want to get intercept 2, what do you do? This value, get it from here. Just it's this one. Read it from here without getting H1. If you are in hurry, you don't need. If I'm asking you get H2, so you know H2 I get it from velocity 2 and velocity 3. You already calculated them here. H1, I'm asking you to get H2. You get velocity 2, velocity 3, plug them here. What is this value? All of this is intercept 1. Just read it from here, put it here. And then what are the missing things in this equation? The missing thing is only H2. You get the H2. But you cannot use this thing alone. Cannot use this thing alone. You need to get these two. This one is simply this equation. So let me go together. Let us see what is this value. Let's do it together. Or T intercept 3. T intercept 3 is equal to what? Who can tell me? So this is T intercept 2. What's T intercept 3? Is T intercept 1 plus T intercept 2 plus 2h3 square root of 1 over v2 squared minus 1 over v3 squared. T-intercept, you get it from here. T-intercept 2, you get it from here. And that's this value. Then the velocities, these two velocities, you get them from so this, sorry, this is 3 and this is 4. 3, velocity 3 and velocity 4. You need velocity 3 and velocity 4. Velocity 3 and velocity 4. That's the mistake I made. Correcting myself. For 3, this is velocity 3 and velocity 4. So you add them together to get the thickness of third layer. Don't worry. Things gonna be easy if you apply them in with some lab. You do it in lab. And then we come to dipping interfaces. Dipping interfaces, things get a bit more complicated then. Let me see how many slides left. God, let me continue with this part. So I talked about horizontal layers. Earth is usually not a horizontal layer. Maybe the layers are dipping. So whenever the layers are dipping, you cannot tell. One shot cannot tell. Yani shooting from one direction, yani the geophones are here and the source here is not enough. You have to make 2 shots. These are the geophones. These are the 5 geophones, 1 source. Make 1 shot here, what we call as forward shot, and make another shot in the other direction. We name it a reverse shot. So this is forward shot, this is reverse shot. So the rays travel the way you see them here. The direct energy will travel straight in both direction. So the slope from both of these lines forward. Why we did again? We do it because that's how the equation is. This intercept includes this intercept. This is actually gives you the not the total depth, but total thickness of from here to here. Thickness is not a thickness, but this gives you the thickness of that specific layer. To add, we need to get the h. Well, that's how the equation works. So for to intercept, we need, this is the intercept 1 plus this value. This one is already there. For dipping interfaces, we usually do 2 shots. One called forward. Geophones are in one direction, the source is in here. We call it forward, and we repeat the shot in the other direction. So the direct energy for both of them travel straight lines because the velocity in the first line is the same, and there is no change in the first layer, in the top part of the first layer. So the slopes will be the same for both shots. The slope will be the same for both shots. Whereas the slope will be different for the refraction, for both forward and reverse. Both of them give you different slopes. Forward and reverse give you different slopes for refractions. Direct is the same. So this is in this direction. If I'm moving this direction, I say I'm moving down dip. I'm moving from here to here. I'm moving down dip. Or if you're moving in the opposite direction, it means you are moving up dip. And the velocity, we call them the slope velocity, we call them apparent velocity. For the refraction, we call them apparent velocity. They are not the real velocities. We'll not do mathematics for this case because it's a bit not easy, especially for deep finding, for the lab at least part. So the velocity, we call them apparent velocity. It's not the real velocity because I'm not sure if there is a dipping or not. And the dip are actually not the accurate velocities. The velocities are not the actual velocity. That's the reason I named them apparent velocities. And we need to do two shots, forward, reverse shots. Each line gives me a different velocity, forward and reverse. Each one gives me a different velocity. So this loop is different than this loop. This loop is different than this loop. This is in here, I'm going down dip, whereas in this direction, I'm going up dip. The dip is decreasing. I'm going up on the dip direction. I'm going down in the opposite in the dip direction. So the velocity of the second layer is not the right velocity. One of them give you a lower velocity than the actual one, whereas the other one gives you a higher velocity than the actual one. So I go to the second. How to get the real velocity? You get the average. You get two velocities, get the average velocity. Gives you something close to the actual velocity. So we'll stop here. Let me ask this question. This is the last thing. This slide explains that going down dip, the velocity is underestimated. You're going down dip, you are underestimating the velocity. The velocity you get is lower than the actual velocity. If you're moving in the opposite direction, the velocity is overestimated. The velocity is the one you get from this one, reverse, because this is up dip direction, the velocity you get is higher than the actual velocity. Whereas moving in this
Should we
direction,
include the angle with velocity or what?
what angle? This one? Yeah,
Yes.
we'll come that to next slide. Next week, sorry. Oh, no, tomorrow, I mean, not next week. Tomorrow, I will explain first before we go to the lab section. And the thickness you get from this intercept is not true thickness. It's this thickness, vertical line. In stratigraphy, we have two thicknesses. This is one thickness. This is another thickness. This is vertical thickness. This is stratigraphic thickness. So you will not get this thickness. You get this thickness, not this thickness. Yeah, perpendicular to the layer from source. This is not perpendicular. Sorry, this is not perpendicular. This is not perpendicular. This is 90 degree. That's the dip you get. So this one gives you another dip. This one gives you another dip. You get two depths. Then you can tell how the line is dipping. You already obtained the velocity from the average. Averaging both of them gives you the velocity of refraction, as we did in the previous So the down dip gives you a lower velocity. Up dip gives you higher velocity. If you're moving from here to here, higher velocity. Down dips gives you lower velocity. You average them to get an estimate of the refracted velocity of the refracted energy from second layer if there is a dipping. Will not include more than one layer because it becomes a bit complicated. And there is no simple way to do this calculation. Then you need different advanced technique and refraction. We will not go to them in this course. For the time being, do you have any questions related to the course or today's lecture at least? Any questions? Anything not clear?
Doctor,
Yes.
from that equation for the intercept, for the time intercept,
Yes.
you mentioned you may give us in the quiz or the midterm. You give us the particular distance. How we determine the which race reach first?
But from the time you calculate,
Okay,
you
how
get
to use it?
so you get, let's assume that that's the equation. And this is the equation. Let's assume that my question is simply, what is the first arrival at some distance, which is 50 meter? What is the type of energy which arrives first? By convention, you know it's not reflection. You say it's either refraction or direct. Am I right?
Yes, Doctor.
So direct, the time of direct is simply this x over v1. You already know v1 from the slope, or you
Oh.
calculated it. Am I right?
Yes, yes.
Or I give you the velocity. Velocity of first layer and second layer are that much to simplify things for you. So you already have this equation and you have this equation. In this equation, I give you probably the thickness of first layer. Then I say I give you the thickness of the first layer. Then I say which one is the first to arrive at this specific distance. So here you plug in number 50. Here also you plug in number 50. I already give you this value. These two values, I give them to you. Provided. So see which time is larger. This time or this time? The larger one, it means it arrives later. The slower one, sorry, the faster time, lower time, it means it's arriving first. Is that clear?
Yes, yes, Doctor.
دكتور الفيلوسيتي كيف نحسبها؟ هل ناخذ نقطة واحدة اكس واحدة على التايم ولا نقطتين من الاكس ونقطتين من التايم؟
نقطتين هنا على هذا اللاين.
يعني كأنه الفيلوسيتي.
هذا يعني بعدين distance على التايم. distance اللي تاخذه من هنا على التايم يعطيك الفيلوسيتي. من هنا نفس الشيء نقطتين. distance على التايم، الفرق في التايم يعطيك الفيلوسيتي. Is that clear?
Yes.
I think it's already shown in hers يعني. You take 2 points. 2 points. Here also 2 points. Okay, I will stop recording first of all. Let me stop the recording.